Okay, kids, so here is the MKS lecture, meters, kilograms, seconds. You'll have lecture notes on them, and I'm just going to kind of go through, point out the things. And so one of the things that physicists had to agree on early on is what are we going to use to measure things? Because if you can't measure quantities, then you can't see if the formulas are right. So after much wailing and gnashing of teeth and rock, paper, scissors, they decided on what's known as the MKS system. So when you look at this, you've got your M, your K, and your S. So you have meters, kilograms, and seconds, okay? So here I've got your basic meter stick, okay? It's about a yard long, one good stride if you have kind of long legs. And so that's about a meter. So that was defined as a division on the prime meridian back when they started the metric system. So here you have your basic meter. And meters is going to measure length. And sometimes you'll see length either shown as like D, which could mean distance. It could also mean displacement. Later on you'll see the difference between those two. Sometimes you just see it written as just X, okay, like a distance, okay, Usually, most of the time, you're going to see it written as D. In some books, they do get really weird, and they'll show it as S. Why? I don't have the faintest idea. I'm just telling you. But what you're going to see most often is a D or an X. If you're talking about a vertical distance, sometimes you'll see that written as a Y value. Okay? So when we get into like projectile motion, we'll talk about what happens in the Y versus what happens in the X. So not a big deal there. Now, kilograms is a measure of mass. Now, here's where mass is different from weight, okay? So here I have a 1 kilogram mass. So there's a couple of ways that you can look at how you define mass. One option in terms of mass is that it's how much stuff is inside this object. So, and that's not going to change. So if I take this 1 kilogram mass to the Earth, or if I take it to the Moon, if I take it to Jupiter, it doesn't make any difference. It's still going to have the same amount of stuff in it. So mass does not change. Weight, which we'll get into later, does change. So weight is a measure of force. So I'm going to just plant this seed now, and we're going to revisit this idea. But weight, when in a physics classroom, when I talk about weight, I'm not talking about pounds, okay? That's how you all are used to thinking about it. Weight isn't kilograms. Weight in a physics classroom is a measure of the gravitational attraction between this thing and whatever rock that you happen to be on. So on Earth, and later on you'll see why this works, but this thing weighs 9.8 newtons on Earth. It weighs 1.63 newtons on the Moon. So force, or weight, is measured in newtons, which we'll get into in just a second. So I'm just planting this seed now. If I want mass, it's going to be in kilograms. If I want weight, it's going to be in newtons. Okay? So you'll hear me preach this again and again and again. I'm just beginning to plant that seed. Seconds, obviously, that's going to be time. Now, so when you look at variables that we're going to use, kilograms for mass is going to be M. Time is going to be lowercase t. This is where you're going to get this confused. And you all sit there and you go, oh, Mr. Burkamp, we won't do that. You lie, you lie, you lie. You're going to make this mistake. So here's what's going to happen. Is that when you see M as a variable, for example, if you have F equals MA, okay, kind of the big dog equation of all big dog equations in physics. That M right there is going to be mass, which is going to be in kilograms, okay? If I want meters, okay, then I would put like distance in there, and then you would substitute meters. So don't confuse M as a variable for mass versus m on the end of a number, which is going to signify a distance. So like if you have 5 meters, okay, hey, that's a distance. If you have F equals MA, that m there is as a variable. And later on, once we begin to do dimensional analysis, you'll very much see the significance of this. So here are what we call the 3 fundamental units: meters, kilograms, and seconds, the MKS system. So in physics, that forms the basis of almost everything that we're going to do in terms of energy, in terms of momentum, in terms of gravitational fields. Every unit that you're going to work with between now and the end of this class in January is going to be some combination of these. That's it. Okay, so that's the beauty of it. Once you can get these down, there's no variation on the theme. It's always going to be some combination of meters, kilograms, and seconds. Easy peasy. Now, out of that, we can get, out of the fundamental units, we can get derived units. So for example, you talk about velocity, right? So velocity is related to speed, but it's not the same thing, and later on you'll see where that difference is. But velocity, the shortcut way to calculate velocity, and there's a whole bunch of different ways you can calculate velocity. But one option is that it's distance divided by time, okay? How far you travel. So let's say that you run the length of a football field, which is about 100 meters, and let's say that that takes you 20 seconds to run that, okay? So here we're going to take 2 fundamental units of distance and time, and we're going to use those to come up with something new. So in this situation, okay, doing a little mental math, stunning, I know, but the zeros are going to cancel out. I'm going to take 10, I'm going to divide that by 2, and I'm going to get 5 meters per second. So this is a rate function. At this point, I'm telling you, you are moving at 5 meters per second. Now, to give you some perspective, okay, isn't like a full-blown sprint, but it's pretty fast. If you're a world-class sprinter, and like you run the 100-meter dash, you're going to run that in about 10 seconds. So world-class sprinters run at about 10 meters per second. But that's world-class. I mean, you are top of the game, 10 meters per second. Mere humans, we're going to run about maybe 7 to 8 meters per second. But again, so when you're seeing a velocity, think of this in terms of a rate function. It's how many meters you are traveling per second. So we took 2 fundamental units of distance and time, and we combined them into something new, which is velocity. Okay. So now we're going to talk about acceleration, and we're never going to talk about the D word, deceleration. We're only going to talk about acceleration. So acceleration is also a rate function. So there's a couple of ways you can express this. One is that it's delta V over time. So anytime you see this delta here, okay, that delta is going to mean a change, right? So you have a change in velocity over time. So if you look at what happens here, you had distance divided by time, which is you end up in meters per second. So with this one, we're going to look at change in velocity over time. So if you look at what happens with the units, and that's one of the things you will hear me say again and again and again and again and again. I cannot emphasize this enough. The sooner you embrace this idea of paying attention to the units in physics, the better off you're going to be. And that leads to a deeper truth that if you focus on the process of how things work and not the product, you're going to go a lot deeper into being actually be able to understand what's happening in a chemistry class, a physics class, whatever it is. Focus on the process, not the product. So to show you how something can accelerate, okay, I've got this little fan cart, right? So I turn that on, and I let go of it, and it starts to rest, and it begins to speed up. Okay, it's accelerating. And oddly enough, if I push it and then let it coast to a stop, that's also acceleration. So notice with acceleration, this isn't saying that you have to be going faster. Acceleration is just the rate at which your velocity changes. Just like speed or velocity is the rate at which your position changes, acceleration is the rate at which your velocity changes. So the other classic example of acceleration is gravity. So I drop this mass and it begins to accelerate. And later on you'll see that that number is 9.8 meters per second squared. It's a very specific number. You will always remember that number. What's the acceleration due to gravity? Oh, 9.8. Everybody remembers that coming out of the physics class. So let's say we're going to look at something simple. So I teach physics and not art, so we're going to draw the world famous carrot car. So here's the carrot car, and we're going to start at rest. So the other way that you're going to see that delta V written, and this is going to be true of any change, is going to be V minus V naught over time. So if you're talking about a change in position, it would be position final minus position, or excuse me, position final minus position initial. If you want to think as the O as being the original, that works for you. Whatever you realize, but this is going to be final minus initial. It's always going to be like this. This will never be V naught minus V. Never, 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 never. It's always going to be V minus V naught over time. That's always how it's going to play out. So, let's say, for example, the car starts at rest, and then it's going to speed up, and let's say that it ends up going 10 meters per second, and it took 2 seconds, okay, just to make up some numbers. So again, 10 meters per second, you're not going to run that fast unless you're a world-class sprinter, and the time is going to take 2 seconds. So my V naught, because I started at rest, is 0 meters per second. So the car was at rest, and then it sped up to 10 meters per second. And let's say that that took 2 seconds. So to calculate that acceleration, my final velocity is going to be 10 meters per second minus 0 meters per second, and then I'm going to get 2 seconds. Now, if you're in a math class, which you're not, but if you were in a math class, I'd say, what's the acceleration? And you'd go, oh, 10 divided by 2, that's going to be 5. And there's your answer. You could write that down, and you would get full credit for your answer. You get an answer of 5. Life is good. But here's the problem. If you just put 5 down in the physics class, I don't know what that number means. I don't know if you're talking about distance. I don't know if you're talking about velocity. If you're talking about ducks, squirrels, the animal of your choice. I don't know what it is, okay? All I know is that the answer is 5. So this is where you have to pay attention to the unit. So we're going to see what can happen here. So one option is that we're going to take meters per second, and we're going to divide it by seconds, and you can sit there and go, oh, well, Mr. Burkamp, the seconds are going to cancel out, and you're going to get meters. And so therefore, the acceleration is 5 meters because the seconds cancel out. Well, number one, that's wrong for any number of reasons, and you'll see why it's wrong algebraically, most importantly. But also conceptually, it doesn't make any sense that we're going to have acceleration measured in meters, and up above, we also talked about distance being measured in meters, and then we're going to have an m here, which is going to be mass. And so we don't have all these m's floating around, and it's just going to be awkward, and it's going to be confusing, and so it's not going to end up as meters. I hate to ruin the surprise, but it's not. But here is what's going to happen. So there's a couple of ways you can do this. It's a personal preference. So one option is you can go, okay, that's meters per second, and we're going to divide by seconds. So instead of dividing by seconds, we can do the magic thing of algebra, and we can multiply by the reciprocal. So the reciprocal of seconds is 1 over seconds. So I've got meters per second times 1 over seconds, and that's going to get us meters per second squared. Okay? So if you're into algebra and multiplying by the reciprocal, that's cool. So we're going to have meters per second squared. Now, what some people like to do, and again, this is a personal preference, the other option is that you can just leave it as 5 meters per second per second. Conceptually, this is actually maybe a little bit easier to understand because you're saying for every second that goes by, this is the rate at which my velocity changes. So I'm going from 0 to 5 meters per second, to 10 meters per second, to 15 meters per second. And every second that goes by, this is how much this number changes. So I've got 5 meters per second per second. If this makes sense to you, go with it. If you like meters per second squared, go with that. What you cannot do is end up in meters, okay? That's the one cardinal sin. And you just can't end up with an answer of 5, because that doesn't make any sense either. So that's the story on acceleration. So here's what we've got so far. If you see the letter D or X, okay, that's going to be a distance, and that's going to be measured in meters. So you could have like 2 meters. We could have mass as a variable, m as a variable, which is going to be in kilograms, which would be something like 1 kilogram. So here I've got like a 1 kilogram mass, which is equivalent to like 2.2 pounds, okay? But again, this is mass, okay? This is mass. This is important. This is mass. It's 1 kilogram. Then you can have time, which is going to be measured in seconds. So it's like, oh, how long did it take for it to fall? I don't know, about 0.2 seconds. So we've got MKS, meters per kilogram seconds. These are the 3 fundamental units. It's like an alphabet that only has 3 letters. Now, out of that, we've come up with 2 derived units. Velocity, which is in meters per second, and then you have acceleration, which is in meters per second squared. Okay, so those are the 2 derived units. Okay, so we've got 3 fundamentals, 2 of the derived. We have one more derived unit to come up with, and that's force. So the big sign in the back of the rim says F equals ma. So let's say that I've got this 1 kilogram mass, and it's going to sit here. And we'll get into Newton's laws of motion later on. But basically, that thing is going to sit there until an outside force acts upon it. Okay? That's what's going to be important, until an outside force acts upon it. So I've got a 1 kilogram mass, and I'm going to make it accelerate, because it's not going to accelerate itself. Because one of the things you'll hear me say is that Mother Nature is a lazy prima donna. Mother Nature is saying, hey, you're at rest, fine, you stay at rest. You want to move, you have to apply a force to it. That's the only way that thing is going to begin to accelerate, is if you begin to apply a force to make it accelerate. So, as simple as it can get, let's say I've got a 1 kilogram mass, and I want to make that thing accelerate at 5 meters per second squared, which would be kind of like that, okay, as a rough acceleration, okay? So here would be a pretty slow acceleration. Oh, that'd be a really fast acceleration. So about 5 meters per second squared would be something like this, okay? So if I want to know how much force that's going to take, mathematically, again, I get an answer of 5. But again, if you just write down 5, that has no meaning, okay? You have to have the units with it. So there's 2 schools of thought that you can do with this. One is that you can just go old school, and you can write kilograms meters over second squared, okay? That's an option, it's valid. If you like that, that's the old school way to do it. 5 kilograms meters per second squared. It works, there you go. But it's kind of a lot of work to write kilograms meters per second squared. So then physicists say, well, what can we do to kind of shorten that up? So one option is that you can go, all right, well, let's look at it from a historical perspective, and Isaac Newton gave us the second law, that force equals mass times acceleration. Oh, so let's measure force in newtons. And thank God his last name was something simple like Newton's. And it wasn't some big, long, Kozlowski Smith or something, I don't know, Kozlowski, whatever. So, or hyphenated into something else. It was just something simple. Oh, 5 newtons. So imagine saying, oh, how much force did it take? 5 Kozlowskis. Oh, dear Lord. Okay? But it was something simple. It was newtons. So the other option is that you can put a capital N. So when you're talking about force, you can either put kilograms meters per second squared, or you can put newtons. It's a personal preference thing. This is the one that you will see most often, but sometimes when you do dimensional analysis, this is handy to use as well, the kilograms meters per second squared. So you've got to be able to work back and forth between the two of these because you'll see both of these used. So to summarize everything that we've got, you have meters, you have kilograms, you have seconds. This is not mass, okay, that's meters, right? That's mass, not force, not weight, mass. You have time in seconds, and then you can combine these into velocity, meters per second, acceleration, meters per second squared, and force, and you can go kilograms, meters per second squared, or you can go newtons. So that's it. There you go. That's the basis of everything that we're going to measure between now and the end of the class. Literally, everything that you are going to do is going to be some combination of these, and even with the newtons, okay, we will not introduce anything new until we get into energy, and that's going to be joules, which is oddly enough a combination of these units. So literally, everything that you are going to measure between now and probably the middle of November is either going to be some combination of this: meters, kilograms, seconds, meters per second squared, or newtons. So there, you're done. You're set for quite a while. So all right, there we go.